Thank you very much for the kind introduction. It is a great pleasure to be here. And I would also like to thank the organizers for the invitation. It's a wonderful place. The topic which I'm going to discuss today, Nickelates. This is the novel class of uh, high temperature or unconventional superconductors discovered very recently in 2019, essentially about 7 years ago. And this topic nowadays is somewhat quite, I can say, hot. There have been many publications appeared very recently. Somehow it doesn't work. No, I cannot switch slides. Somehow it doesn't work. Okay. This is some kind of my motivation, and at the same time, this is the outline of my talk. Yes, I mentioned that, yes, the problem somehow appeared very, very recently, that there was a great breakthrough, experimental breakthrough made in Stanford. The people managed to synthesize this infinite layer Nickelates, and somehow by construction, they obtained superconducting materials with somewhat not very high temperature, but it was a real breakthrough which starts this somehow very hot investigation. Basically, well, in the first part of my talk, I will focus on the infinite layer nickelates. These are somewhat specific nickelate materials with very specific crystal structure, which are somewhat isoelectronic and isostructure to infinite layer cuprate superconductors. I would say that physics of superconducting physics in nickelates in much respect somehow related to cuprates and also to, in some sense, to iron-based superconductors. Although in the beginning people claimed that no, this is somewhat very new exotic materials which show some kind of exotic mechanism of superconductivity because of rare earth elements. And in the second part of my talk, I will switch to more somewhat these are thin films materials to bulk materials under pressure. This is somewhat a very recent achievement made in 2023 or 2024. Many papers were published in Nature, some Nature Communications, etc. Some Chinese groups, they managed to first to perform synthesis of really somewhat pure rather than copper nickelates, and then they realized that under pressure, those materials exhibit quite strong superconductivity. Transition temperature nowadays is about like 80 or 96 K. I mean, this is somewhat from some optimization of crystal structure, some slight doping, because these materials, like by synthesis, it's to synthesize them, it is not that simple. Sometimes introducing some disorder, some doping, some even isoelectronic doping of such materials tends to stabilize somewhat homogeneous crystal structures, and those materials show somewhat really nice superconductivity. Okay, and this, yes, I tried to summarize somehow to plot on this famous graph all these recent results somehow, and it is some kind of rise up in TC. Those materials are somewhat very promising in terms of experimental studies. I would expect that this is not yet the limit in terms of TC. Nowadays, the most focus is some kind of switch to rather than thin films phases. Some kind of people try to stabilize superconductivity at ambient pressure. And there are some promises like claims about superconductivity with relatively high TC, like 40, some 50 K, but with no external pressure. Okay, my first part is about hold up infinite layer nickelates. As I told, yes, this achievement, this real breakthrough was made in the group by Harald Wong in Stanford very, very recently, some 6 or 7 years ago. it's some kind of real chemistry, some kind of complex chemistry. They try to synthesize these infinite layer systems. Why? Because of they are somewhat isoelectronic and isostructural to infinite layer cuprates, which shows some quite a strong TC about 100K upon hole doping. That's why people claimed, okay, if you would be able to some kind of synthesize these materials, then probably those materials will be superconducting. It took, I think, decades to be able to synthesize clear infinite layer systems because of, yes, this is like layer by layer growing of perovskite phase and then some reduction, some soft chemistry, topotactic reduction with some chemical substances, they some kind of cut apical oxygen. And this is very non-trivial technique in the sense that uh, to me it is like a mystery that they managed to obtain some kind of clear, some homogeneous thin films. And it was some kind of realized that as like 10 nanometer, about 10 plus minus nanometer thin films synthesized with this soft apoptoctic reduction shows superconductivity. Although TC is somewhat small, about 15K, it was realized that under pressure, upon hole doping with strontium, it was realized that it is quite tunable. It's under pressure, so like 10 to 20 GPa, it reached to 30K. Of course, yes, those materials must be, thin films must be as soon as possible clean, and this is somewhat very nice result. Superconducting thin films covered with, yes, they grow on strontium titanate and covered again on top with strontium titanate to make it more homogeneous because of, yes, these thin films are somewhat metastable to some kind of stabilize the crystal structure of these materials, but you may see some kind of that synthesis is quite problematic. You might see some kind of defect structure. It's just clear this is STM tunneling measurement along the z-axis, and they show some kind of inclusion, some completely different phases like either stacking fold or excess of oxygen. It's not that simple to remove all the apical oxygens from the system, from the perovskite phase. And the story about hydrogen is even more some kind of complex because of hydrogen is particularly difficult to detect in the crystal structure. But people somewhat managed to synthesize those materials, and it was somewhat surprising that from the beginning they see clear phase transition to yes, clear superconductivity, yes, resistivity drop to zero, and upon some application of magnetic field, and those materials show, yes, they see this rise up resistivity, Meissner effect. I mean, this result immediately, just in 1 or 2 years, was well reproduced, appeared very many different systems. Although I think about 5 or 6 groups are able to synthesize those materials in the world. This is, yes, somewhat problematic, yes, not easy to synthesize them. And at the moment, yes, somewhat there's some kind of unclear point about these materials, that superconductivity was found only in thin films. Of course, I can say about some, okay, those thin films are somewhat strained due to this growing on top of strontium titanate. They experience some kind of a pressure. You pressurize somehow this square lattice of nickel ions, and this acts some kind of external pressure. What is surprising that, yes, superconductivity appears only in thin films, although in bulk, no evidence at all. I mean, there are some nowadays very nice samples, bulk samples of infinite layer Nickelates, doped, undoped, all of them showed no evidence for superconductivity. Another story is about this long-range magnetic order, some kind of in twist towards cuprates. Is there some kind of long-range ordered state which we suppressed with some doping, etc., and it leads to superconductivity? No evidence at all. All these materials and thin films and in bulk materials, they show for the moment. And probably this is related to the crystal structure that they're still somewhat imperfect. And we need to some kind of to improve synthesis to reach some kind of quality, high quality samples, which would show some magnetic ordering. But the last point I don't understand at all. It was shown quite somewhat couple of years ago. I even contacted these guys from, I think, Switzerland. They claimed that they managed to synthesize very many different bulk materials, and all of them show this universal spin glass behavior. Although this is some kind of a hint of frustration. Although they claim that there are no some kind of defects, they're very pure, very nice, undoped systems, and all of them they have square lattice of nickels and of nickel ions, and this is somewhat some kind of unusual. This is just to show us that all these experiments, they were well reproduced, they show perfect diamagnetic response, very clear evidence of superconductivity, even yes, somewhat similar to cuprates, they show this change of the hole, some kind of electron to hole to yes like behavior in the hole coefficient, yes, some kind of, and this in the normal state, and this somehow related in some sense to the, if you would extrapolate, yes, it is related to some kind of middle of this dome, superconducting dome. I mean, this is some kind of a hint that upon doping in this system, there is some kind of a crossover between some in 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 transport properties. I mean, some kind of some smoking gun or Flisch's transition that somehow again some electronic structure changes upon doping and some possibly magnetic some fluctuations or some tendencies to some kind of some competing magnetic states that also somehow change upon doping. Well, this is some kind of summary of many experimental results. Well, I wouldn't say much about shown here weakly insulating behaviors. This is just imperfection of all the samples. I would say nowadays this state is more metallic, thermoliquid like. This one is more like some kind of there is some possibly short range magnetic order, but not the long range one, and some kind of also possibly more metallic than insulating. And this first claims they somehow connected to the problems with all these samples. What is somehow clear that this TC about 15, there have been many materials synthesized. And in the beginning, I told about that some exotic microscopic theories to explain this superconductivity because of these the first yes, I think here the first synthesis was done for neodymium. I mean, some kind of people claiming about that, okay, probably as 4f electrons are involved in this superconductivity, probably Kondo effects of Kondo screening of some local magnetic moments. And yes, there's some kind of a new type of microscopic mechanism behind this superconductivity, but recently it turned out that not the case at all. People managed to synthesize nickelates, this infinite layer nickelates with lanthanum, strontium, and calcium without F elements at all. And they show the same properties. This is absolutely the same. Superconductivity with TC about 15, the same behavior for Hall coefficient, that it changes a sign, some kind of clear evidence of this some kind of a bit anisotropic dome, superconducting dome, and even some tunneling experiments, they were not somewhat consistent in the sense that some experiments, they show evidence for D-wave superconductivity, others showed S-wave superconductivity, although some samples, they showed the mixed S. This is some kind of still ongoing research in many respects. What, as a theoretician, what we can say about the electronic structure of these materials, and this is our starting point. Some just that the density functional theory can tell us about this system in comparison to cuprate analogous to this infinite layer system, to infinite layer systems. And this is just a plain calculation without no correlations are involved. These are metals. You see some kind of like in cuprates. You see this hole-like, large hole-like surface sheet around the endpoint. Also here, what we do see that the electronic structure in case of nickel is somewhat more complex in the sense that there is a self-doping due to this shift of the rare earth 5D states. They shift below the Fermi level and they start to contribute to the Fermi surface. And this is the first point. The second point is that the oxygen states, they appear somehow deep below in energy, and it means that this material more behaves like a mode type system, although this is a charge transfer insulator. As soon as you introduce correlations, it will become an insulator. This one possibly not, due to this some contribution at the Fermi level to the rare earth states, D states. And yes, in the beginning, people claim about that, yes, in the first paper, there is no Jankrais singlet states in this spectroscopic properties, and possibly spin fluctuations are not somewhat so important, but these were somewhat first claims. And I would say the present understanding is that these materials are, in fact, much closer to cuprates. They appear somehow in between cuprates and iron-based superconductors because of some kind of multi-orbital Fermi surface. They somehow resemble, in some sense, iron-based superconductors. In terms of renormalizations, some kind of strong correlations, they're more similar to cuprates. Well, this is what somehow, as we would like it to start this problem, or as possible at the time when, yes, the first papers start to appear, and we were possibly the first one who somewhat claimed about this, that upon doping there is some kind of a quite strong change of the spectral function. This is our some plain T plus dynamical infield theory calculations of the electronic structure, how it looks like. This is just a machinery. I'm not going to talk about how it works. This is what we can do for the top of what we can do for real materials at the moment. There are no vertex corrections, no some kind of non-local correlations. Every physics is local. All non-local physics comes from density functions here. Well, we do see some kind of, as these are the Fermi surfaces, and this paper essentially was published together with our next speaker, Sergei Skornikov, and what we do see some kind of a change of this Lifshitz transition, and those two orbitals somehow involved, the planar x squared minus y squared and z squared orbitals. They show all strong orbital selectivity with strong renormalizations, which differ like 3 times. And we do see a clear Lifshitz transition of the Fermi surface, and so possibly associated with, I will show in the next slides, associated with the construction of magnetic correlations. Basically, what we do see that there is a Fermi surface which has a perfectly somewhat nested nested in the AB plane, and of course, because of this, there are some kind of magnetic correlations. Possibly there are several tendencies, as we see, and they complete each other. And possibly because of this, there is no long-range magnetism, although short-range correlations. And this is our comparison somehow to the experiments. Very recent experiments. They appeared just last year. Somewhat all our somewhat calculations for the intermediate to doped system, they just almost coincide in many respects. The people see this large Fermi surface due to this nickel planar xy minus y square orbitals, some kind of yes, and physics which is somewhat related to cuprates, and even renormalizations there somewhat close to those which we obtained. Some kind of this results appeared somehow in 5 years after our publication, but on those thought this is a nice support in many respects. As I told, yes, this is our calculation of the quasi-particle Fermi surfaces, how the quasi-particle Fermi surfaces behave with doping, and again, using the best machinery. What we do see that some kind of reconstruction of the Fermi surface, and what is the most important, that we calculated this non-local spin susceptibility, which shows some kind of a tendency to some kind of magnetic state, some kind of ordering. In our paper, we mostly focus on this interplay between these 2 points, M and A. M is related to the standard Niel type ordering. A is the Niel type ordering. M is a planar, some kind of purely planar antiferromagnetic state. Somehow we missed this interesting behavior somewhere here for the intermediate doping state, that in fact upon this optimal doping we do have some 2 incommensurate magnetic states which compete each other. And I would say that this behavior we do see now that this behavior is quite common for all Nickelates, for infinite layer Nickelates, for others than popular Nickelates. We do see that Lifshitz transition upon doping results in this reconstruction of magnetic correlations. They change quite drastically, and this is some kind of a smoking gun of competing in planar spin or charge density wave correlations. This material somewhat show strong tendency, some kind of to competing magnetism or to competing charge density wave formation. And this is, yes, some kind of, the idea was a bit simple, okay. But the first time that when we focused on this interplay between these 2 points, we try somehow to, okay, what our machinery can done for magnetic ordered phase, just in dynamical infield theory. We try to evaluate this 2 simple, they're not that simple, there are many different magnetic states. And on the density functional level, it was some kind of boring. All of them are nearly stable. They compete each other somehow, but nothing essentially happened upon doping. Although in dynamic and infield theory calculation, I think this is like we pump some correlations, some local fluctuations in the system, and these local fluctuations somehow change the Fermi surface and they improve the magnetic state somehow. What we end up some kind of magnetic phase which drastically dropped to upon some slight doping to at 0.1 holes. And we try to somehow to this is like room temperature calculation. We try to go down to I think less than 100 K. We didn't manage to find out any magnetic state here, just at the optimal doping. Although upon large hole doping, there is a transition towards the M state, some kind of a planar differomagnetic ordering, like we received this in our susceptibility calculations. And I would say that can experiment somehow tell us about magnetic excitations, and these are some relatively recent results published in very nice journals. But I would say that these results are still somewhat a bit inconsistent in the sense that it really depends on the samples. People somehow use the same 10 nanometer thick Nickelates, but what differs is that these materials somewhat covered with protected layer on top, and they show very clear some kind of paramagnon spectrum, some kind of this is like spin 1/2 antiferromagnet in undoped case, well, with relatively large exchange couplings, and we were the first who obtained this large value on the market. People claim about essentially 10 times lower values. Although in our case, yes, if we would be honest, we obtained some kind of frustrated case, frustrated magnetic state, but these guys claim that there are no frustration, that paramagnon line goes down here instead of up, and this is like a typical spin 1/2, and this is somewhat a subject of our interest. The same, absolutely, or everything the same experiment, but for non-capped Nickelates show completely different. Although people claim that there is no clear evidence of dispersive spin wave excitation, I do see some kind of paramagnon-like behavior here, but what is the most important, they seen some kind of evidence for let's say either CDV formation with unusual vector Q1/3 some kind of this is along I think the nickel oxide bond. Although yes, nowadays this result is somewhat under the question because of as a possible explanation is that due to this synthesis, there is some kind of a long range superstructure modulation due to oxygen, that it's some kind of oxygen defect tends to somehow to order in the lattice, and that's why because of this ordering, yes, there is some kind of some quasi-elastic result, quasi-elastic peak here, which in the beginning was claimed to the formation of the CDV phase. Our answer on this question, we try to model this behavior somehow. This is some kind of a combination of different techniques. We try to optimize the lattice. And it turned out that lattice is pretty much important for this material. I mean, to stabilize waste, some kind of tiny lattice deformations. But those tiny lattice deformations, they result to some kind of ordered phase, which we call bond ordered phase, shown here. This, on the first glance, this is some kind of very unusual, some kind of combination of spin and charge density wave. But I would say this is a typical behavior for Nickelates. I mean, for lanthanum-2 nickel O4 oxide, doped oxides, in which upon doping you can obtain a zoo of very many different magnetic states, charge-ordered magnetic states. And we some kind of reproduce one of those. What is particularly interesting that this formation of ferromagnetic zigzag lines, like in doped manganese, doped charge-ordered manganites. Yes, this is a lot of fun. And upon doping, yes, all our calculations, both functional and dynamical for CLI calculations, show that this ordered phase becomes more stable, progressively stable upon doping with whole dopes, on doping with holes. And this is some kind of, I decided to also to show results of our colleagues. This is somewhat what our colleagues from Hamburg, this is possible from Hamburg, has tried to answer about what's going with magnetic excitations in this system. This is some kind of a combination of dynamical mean field theory and random phase approximation to relate both these either superconducting tendencies or this paramagnon-like spectrum, and the results are somewhat quite impressive in comparison. I would say not that bad. And what is somewhat important is that they do see this x square minus y square wave superconductivity similar somehow to Cooper rates, although it competes somehow to nodal S plus minus state. And because of some kind of tuning, fine tuning, it's possible to switch a bit between yes x squared minus y squared S plus minus. This is our colleagues from Vienna, Carsten Hell group, and they try to apply this dynamical vertex approximation. So Alexei mentioned today, this is one band system. I mean, there's some kind of uncertainty about that. There's still no clear understanding what is the low energy model for this material. Is this just one band is enough, or one band plus some charge reservoir, which is uncorrelated, or you need to have at least some two bands, two correlated bands, somehow coupled to some charge reservoir. In our case, in our dynamical infield theory calculation, we don't care about this at all. We use just all 5 bands, and that's it. Here it is quite problematic. You can all this calculation can be done only for one band for the moment. Although the calculations are somewhat very nice, nicely reproduced this magnetic excitation behavior, and even show this some kind of asymmetric superconducting dome upon hole doping in these materials. Yes, so probably one of the last slide on this system that somewhat different method. I mean, many different approximations used to show that in principle, near to optimal doping, this is possibly x squared minus y squared wave superconductivity in this material, similar to Cooper rates in some respect. Although at high doping and on some fine tuning, we can reach S plus minus superconductivity multi-Fermis. You need to have several sheets of on the Fermi surface. This is somewhat similar to, I find similar to iron-based superconductors. And there was and even somewhat funny story about this, that in principle we need to dope this system to make it superconducting, but there are many possibilities how to do this, and one of those possibilities to somehow to grow up this material, some kind of 6,5 oxygen 12, which would have some kind of by construction the optimally doped state, nickel state. And people would manage to synthesize this material, and indeed it showed superconductivity with TC about 13K, somewhat consistent with all the previous series of infinite layer Nickelates, some kind of that, yes, indeed, we need to dope the system somehow to achieve some kind of optimal doping, which is related to some maximum of superconductivity in this material. What is somewhat hidden problem in all these materials somehow which unify all of them? You know nothing about hydrogen. And this is a real pain. In principle, there are several years publication appeared in Nature very recently that possibly there is a lot of hydrogen dissolved in the system, like 20%. No one knows the answer in principle. This is a hard problem somehow to determine amount of hydrogen. And even some theoreticians even explained that, okay, we need hydrogen to possibly hydrogen is quite important, yes, to stabilize superconductivity in this material. That's why, yes, at this moment, I twist to completely somewhat similar systems related to these infinite layer Nickelates rather than proper phases of Nickelates. Why? First of all, these are bulk materials. There's no hydrogen involved to synthesize them. But you need to pay external pressure to make them superconducting. And very, very recently, like 2 years ago, people managed to find out superconductivity is in double layer and three layer Nickelates, which are entirely mixed valent, 2 plus, 2.5 plus, 2.67 plus, 2 and 2/3. Although this single layer Nickelate is known for decades, it is some kind of a multi-insulator with large energy gap, and it really needs to apply a lot of either you need to either to dop this system or pressurize heavily to make it somewhat metallic. I do not know actually any results to make this system metallic. Immediately, yes, consistent results that upon external pressure, this material undergoes some kind of structural transition associated with suppression of some kind of ordered phase, possibly as charge density wave or spin density wave ordered phase. Now it is some kind of, there are some still debates about the origin of this phase. You end up in superconducting domes, strange metal behavior, and all these results were immediately reproduced in single crystals, in polycrystals, some very many different groups. Somewhat, even it is somewhat surprising because present people start to some kind of to pay attention to this delta to deficient of oxygen in this material, and it is as high as sometimes 10%, but still these materials exhibit superconductivity, although there are some issues about somewhat parent phases. Yes. Well, we also were somewhat fast enough to focus on this material that physics is somewhat now a bit different. We have a different valency, 2.5 plus valency, and we have two nickel sides on top of each other. I mean that it turns out that now some kind of bonding, anti-bonding, some kind of physics involved in this in the low energy physics of these materials. I mean, so at the Fermi level we have 4 states. Basically, we have 2 sides, 2 each states on each. We have in total four states, but this bonding z square orbital state, it appears somewhere here, just near below the Fermi level, touch the Fermi level at the M point, and it seems it fully occupied. We end up with x square minus y square orbital, which appears somewhat on the Fermi level. We have the same story with Van Hoff singularity, which is close to the Fermi level in the X point. We have strong incoherence of the spectral weight. This is like when strange metal behavior, strong correlations like incorporates. And it is somewhat also remarkable that in this gamma X direction, we do see that this is some kind of z square, antibonic z square orbitals, but these 2 x square minus y square orbitals are split each other, and we end up with half field state, but in the path of the Brillouin zone. And this is possibly the origin of strong correlations in this state. I mean, there is some kind of, again, smoking gun that non-local correlations will be pretty much important in this material, like in cuprates. I mean, at the moment we are not able to somehow to answer this question about non-local correlations, but possibly in the future somehow we are trying to work on this. Well, this is again the story about renormalizations. This material show strongly orbital dependent quasi-particle renormalizations. So this EG state, again nested Fermi surface, although we do see some kind of very incoherent state due to this z-square orbital which touch the Fermi surface near to the endpoint. Well, the same idea. Spin susceptibility without Sasson bubble approximation, without vertex correction. This is what we can do at the moment for real materials. Again, some kind of competing states. Yes. Uh, Evidence for some kind of in-plane spin charge density wave correlation, strong fluctuations, and possibly superconductivity is somehow connected or driven by these fluctuations. Even that, this is what's somewhat a very, very interesting, very recent result that I tried to somehow to tune how this susceptibility depends upon the stopping. And the result is somewhat, yes, on the first glance, this is somewhat expected result on the what highly unusual, I would say. If we would heavily top the system, we end up with nickel 2 plus site, not 2 plus ion. Well, we end up with some kind of long-range magnitudes. There's some evidence. Although the system is somewhat under pressure, that's why it remains metallic. I mean, we need to have a Fermi surface to compute this KFQ. As soon as we dope nickel 2 plus ion with holes, we go in this direction somehow. We get some kind of two competing states, incommensurate competing states, some kind of, I interpret this behavior as some kind of stripe phase, spin charge density stripe state. It ends up to at zero. This is nickel 2 plus, 2.5 plus ion. This is what some kind of superconducting state. I mean, this very simple, very naive consideration, we can interpret like if we would dope nickel, this system, with electrons, we rise up magnetic fluctuations in this system. Possibly this is the way how to tune superconductivity in this material. So this somehow on the way I ask our colleagues to focus on synthesis of cerium doped to delay systems. Although upon hole doping, at some point we undergo a Lifshitz transition, which renormalize somehow magnetic correlations, and the system somehow results in something else. I mean, we do see some kind of in short doping regime, like some kind of increasing of spin fluctuations upon electron doping. And of course, if you dope it heavily above 0.2 electron, there is yet another phase, yet another Lifshitz transition, which modifies the Fermi surface. It becomes more three-dimensional-like, and this possibly breaks superconductivity in the system. This is our comparison for the moment to the experiment, to the ARPS experiments, and this is what we have on the market for the moment. And I would say for this distorted phase, I mean for the parent phase, this is our result. I think comparison somewhat, yes, more or less fine. This also, yes, spectroscopic estimates of quasi-particle renormalizations give us somewhat similar numbers, although that they, for the Z-square orbitals, they showed some kind of big discrepancy between like 5 and 8. In our case, we do have like about 4 and 5. Yes, but this somehow contradicts to transport measurements. It shows some just 2.1. Yes, of course, all this data somehow is very sensitive to non-stoichiometry, and in some cases, yes, it results in a shift of this critical pressure, some etc. So kind of even people they don't manage to reproduce in some samples this zero resistivity state. We do see some kind of the presence of some extra phases like nickel oxide, which somehow modifies this result. Yeah, this is about spin density wave ordering. This is somewhat very recent results. Somehow 1 or 2 years ago. Two different techniques show relatively similar behavior, that there is some kind of tendency towards some kind of a combined spin charge density wave state in this material, and strong uh, interlay superexchange coupling, and some kind of uh, similar that we discussed for infinitely Nickelates. We managed to essentially to repeat the same calculations which we done for infinite layer system, but for now for this material again, we combine both density function plus halves the static mean field to optimize the lattice. Lattice distortions are somewhat small, but they're somewhat quite important. We find out very many different magnetic states, but it turned out that the most stable, I would say, in terms of internal energy was this one. Again, the same story. We have some kind of zigzag chain of ferromagnetic chain of some kind of nickel 2 plus, nickel 3 plus. I mean, differences are somewhat small because of this is some kind of a mixture between side ordered and bond ordered phase state, some kind of. But yeah, there's in the parent phase there's some kind of most possibly this phase realized in this material. Concerning the mode state, this is still somewhat a tricky question, I would say. In our case, we apply the most the most crude approximation. We use just tight binding model to be able to obtain mode insulating phase for in this spin polarized dynamical and full sphere calculus. As soon we do this self-consistently as usual, we end up with some kind of site selective mode insulator, and these electron deficient side become paramagnetic. We still have some localized spin and some kind of strongly localized paramagnetic and nearly metallic, and these are somewhat localized and nearly insulated. Some kind of some kind of unusual electronic state, and it becomes in total somewhat a bad metal. I would say if we interpret this as somewhat, well, the system is somewhat at the verge of the metal, so the phase transition, but most probably it is somewhat metallic. But yeah, but it really depends on yes. Concerning superconductivity, this is somewhat a mixed summary of different techniques. It is a pity that all these techniques are somewhat still very approximative. I mean, some RPA, TJ, Flex, all this material, all these approaches somehow remain perturbative. I mean, the best would be, of course, to do possibly dual fermions. And this is our, long-term vision for these systems. And we even discussed with Alexei, and we have some plans. Somehow we are working on this. But the main result is that for these materials, we do have this S plus minus superconductivity, possibly with a mixture with this state, and this pairing symmetry is quite sensitive to fine-tuning somewhat, but I would say that the most common result now is that this is somewhat S plus minus superconductivity. And this aspect, again, this is somewhat I found a very nice paper by Thomas Meyer about just Pillay-Hubbard model. And he claimed about 3 years ago, he computed just a model, and he tried to tune some kind of Fermi-surface to top it. And he claimed that as soon one of the Fermi-surface sheets disappear, this leads to a rise of superconductivity in this material. If we would top this material with electrons, we remove this Fermi-surface sheet. And possibly this is the way how to pump superconductivity in this material. Yes, and this is a 3-layer system. I would say the physics is essentially the same. The only thing that we have somewhat different bonding states here, that bonding splitting. Now we have 2.5 singularities due to some kind of top layer, bottom layer. And physics is essentially the same. Fermi surfaces are near the same, although we do see some kind of three-dimensional like Fermi surface around the gamma z direction. And this top and bottom layers, they show some kind of behavior like in P-layer system, although the central one is less correlated and somewhat more, I would say, frustrated. There's no some kind of clear, some kind of magnetic state. Yeah. And I don't know. Yes, I think I'm about in time to finish this talk. Yeah, I would say that these materials are very, very promising, and to say some kind of physics related to cuprates. It gives us somewhat opportunity to study unconventional superconductivity paths in under different somewhat direction. There's different materials. Now we have somewhat different Fermi surfaces, although some again spin fluctuations seems to give us this superconducting glue, which is responsible for these anomalous properties of these materials. I would say what is quite disappointing for me as a theoretician that we still don't have methods to be able to solve these materials. I mean, honestly, what we have done for the moment, yes. Now in dynamical meaningful theory, we can compute the normal properties of these materials. Okay. But to say something about superconductivity, there is essentially no way. We still use RPA since essentially 90s. We still use flex essentially with beginning 2000. We still use TJ model. All these methods, they're somewhat approximative, and we do see that these systems are close to this orbital selective localizations, and not necessarily that it is okay to use these techniques. I would say the main achievement was done by experimentalists who managed to synthesize all these materials. Thanks to the experimentalists, but we still need to work a lot to be able to explain the properties of these materials from a theoretical point of view. Although we have some hints now. I say to the experimentalists, okay, so let's try to synthesize such compositions, and possibly superconductivity will pump superconductivity in this material. With this, I would like to thank you for your attention, and just to, yes, we are running this Russian Science Foundation project on Nickelates, and now we do have samples, powder samples for all these materials, even some top tiers, and if you have some ideas what to measure, yes, possibly we can provide you those samples.
Okay. Let's sense our chip. The paper is open for discussions. Any questions? Good.
Your slides. So you presented a couple of three states, right? Like bond order, something like that. Yeah, this one. Yeah. So the first question is actually, so which one? So you underlined one of those.
Yeah.
So it is because that one has lower energy.
Yeah.
Okay. Good. And then so you have order like down, up, down. If you go straight along one of the nickel line. So is this because of the like next nearest neighbor exchange?
Possibly.
And the other question is so you probably calculated all correlators. So I mean spin for instance correlator. Yeah. So how should we think about this system? Are spins localized? And correlator is like Heisenberg-like, or
This is a good question. All these materials, they show some kind of tendency to localization. I mean, they are not some kind of localized as some mod systems, but they're not delocalized like in purely itinerant system. They show some kind of, yes, decay of this kind of toe, and but
So what is the lifetime? If you
we didn't manage to we didn't estimate lifetime.
thanks.
Thanks a lot for this very, very impressive survey. I'm sorry to ask such a stupid question, but what is about phonons?
What
Other phonons?
moments?
Phonons. What,
Phonons.
is there any evidence for conventional superconductivity in this system?
Well, this is also a nice question. I would say, can we compute phonons for a material which is close to some kind of localization limit or some kind of exactly this intermediate? I would say there are some claims that people, they use density functional, some non-magnetic calculation to relate electron-phonon interaction strength, and it was too small to reproduce any superconductivity. I would say the estimate was less than 1K. So
I see.
0.1K.
Experimental wise, is there some isotope effect or?
I'm not aware of such an experiment. I mean, this is a relatively recent systems, and possibly this is a good.
I got your first claim. Yeah, if density function gives nothing, then probably there is nothing.
I would say the answer, I do not know.
Okay. Thank you.
Any more questions?
So my questions will be as an outsider. I wanted to know if there are any experiments with THVA or Fermi surface measurements.
Can you speak up a bit because of, yes, this is like interference. I don't see.
Are there any Fermi surface measurements?
Fermi surface measurements. Well, for the parent phases, yes. Although this is somewhat tricky. Yes, this is like yes. Formally, this is the Fermi surface measurement. This one is the experiment for the parent phase, ambient pressure, some kind of ordered phase. But I would say that some experiments, transport experiments, they claim that the system is close to some kind of an insulating state. But people measure the Fermi surface here, some kind of renormalizations, etc. I mean, the main it coincides quite nicely our results somewhat. If we neglect some this density wave, etc. state, just I would say more or less a good agreement. Although this experiment was done, I think, at relatively low temperature, possibly very close to this density wave phase. This what I still don't quite understand. There are some kind of qualitative uncertainties for these materials, and the main issue is that only now people start to somehow to publish data about oxygen non-stoichiometry of their samples. It varies very dramatically, I mean, in 10%. And possibly, yes, these are somewhat oxygen deficient samples, which are metallic, which show some kind of possible short-range correlations. I mean, short-range density wave, which some kind of don't really renormalize the Fermi surface. I mean, the charge density wave should somehow open a gap on the Fermi surface, or some Fermi surface sheet should somehow disappear, at least one of them. There are no clear experimental evidence of this. And even some there is no some kind of correspondence between transport and spectroscopic measurements. I mean, based on transport measurements, people more claim about insulating state at somewhat for ambient pressure, low temperatures. Although people who are doing spectroscopy, they claim about some kind of metallic state, although it is short-range density wave with no some kind of long-range ordering.
I got it. Very interesting. And second thing is, are these mixed valent substances I might have missed? You might have mentioned.
Say again, what?
Are these mixed valent?
Mixed valence. And what do you mean by mixed
Is there
valence?
valence fluctuations in nickel?
Oh, I'm. What do you mean by valence fluctuations? I mean, there is some tendency that those materials exhibit some kind of tendencies to charge density wave formation. And in that respect, yes. But there is no some kind of tendency like in heavy fermions when this valence fluctuation would lead to some kind of strong renormalizations or whatever. This I don't see
Okay.
at all.
More questions?
I have a question.
From the core.
I have a question too. So how does TC of the thin film samples that show superconductivity at ambient pressure depend on the film thickness? How does this TC depend on the film thickness of the materials in your first?
I'm talking about the first part.
First part, yes.
The first part. So I'm not sure that there is some kind of some increase of TC. Of course, there is some critical thickness like 4 or 5 nanometers, and then TC is roughly like similar, like 15K. And then I've seen people went to 25 nanometers, and it was nearly the same. But then there's some kind of issues with structural homogeneity. I mean, there's some start to grow up some other phases like nickel oxide phases, which start to destroy superconductivity. This is a nice question in the sense that there is some particular way to tune superconductivity because these are all layered system, and you can to grow up some kind of heterostructures. And people, yes, manage to do this for infinite layer system. They really grow some kind of heterostructures that they're superconducting with some, again, critical thickness of this infinite layer system. Also for radix and Popper phases, there's some kind of zoo of many possible, yes, states. Like you can put one layer on, and then two B layer, again one layer, and B layer, and either three layer, some three layer phase, which is somehow twist with one layer. And there are some possibilities for heterostructure in these materials. Most of them show, yes, superconductivity as soon as you have a nice crystal structure, homogeneous crystal structure.
What about below 5 nanometers?
Below 5 nanometers,
Is there any?
I think there's no superconductivity. I think below 4 or some about 3 nanometers, I think there's no superconductivity, something like that.
And after 25?
I'm not completely sure, but as far as
More questions?
Even your calculations give a nice coherent distribution of the spectral weight at the Fermi level. So, but at the same time, renormalization factors are rather high. Did you check Fermi liquid behavior?
Oh, I didn't. What it looks like, well, what is not Fermi liquid? This is a somewhat tough question in some sense. You can, yes, to check how it behaves with temperature. Yes, this is true. We didn't try.
More questions?
Okay, thank you for your report again. And I have a question. In the end, you said that as a theoretician, you're upset because we don't have some models which describe it. And for instance, TJ model is insufficient. Why do you think so? And which properties should model have to describe this phenomena?
My personal opinion that the best way would be to pump all correlations like local and non-local, and to see only one way, one robust and kind of straight way, yes, to do some dual fermions. Probably I'm wrong. I don't know. All these models, TJ, whatever models, you somehow you cut your diagrammatic series. Either you forget about some charge fluctuations or some kind of treat some spin fluctuation some particular way, neglect by this, by that. We are working in the limit when possibly all diagrams are. And,
So yes, computationally, it's very costly.
there is no free lunch, my science advisor, Dieter Forhat, he always claimed there's no free lunch. We are not able to solve the full Hamiltonian. We need to somehow to cut some particular either fluctuations or charge fluctuation or some cut spin fluctuation to be able to diagonalize this Hamiltonian. There's no way.
Okay, thank you.